In this module, we introduce the concept of isomorphism between two graphs and automorphism of a graph. Two graphs x1 and x2 are said to be isomorphic if there is a one-to-one correspondence between the vertex set of x1 to vertex set of x2 such that adjacency relationship is preserved. If two graphs are isomorphic, then they are same. That means they have same number of vertices, same number of edges, etc. So, if you are able to show that at least one property not shared by these two graphs, then they are not isomorphic. So, it is often easy to show that two graphs are not isomorphic than showing the graphs are isomorphic. In the module 5, we will see graph isomorphism and automorphism group of a graph. The objectives of this module are isomorphic graphs, self-complementary graphs, automorphism group of a graph and asymmetric graphs. Graph isomorphism problem. The graph isomorphism problem can be easily stated. Check to see if two graphs that look differently are actually the same. The problem of determining whether two given graphs are isomorphic is an old problem and it has many applications. Example, in chemistry, listing all molecules in a certain class. All attempts to find a collection of easily computable graph parameters that are sufficient to distinguish any pair of non-isomorphic graphs have failed. This problem occupies a rare position in the world of complexity theory. This problem is clearly NP, but not known to be in P. It is not known to be NP complete. Many subdisciplines of mathematics such as topology theory and group theory can be brought into bear on the problem. Yet only for special classes of graphs polynomial time algorithms been discovered. Definition of isomorphism of graphs. Two graphs x1 equal to v1 e1 and x2 equal to v2 e2 are said to be isomorphic to each other if there is a mapping, there is a function f from vertex set of x1 to vertex set of x2 such that f is 1 1, f is onto, and for each pair of vertices u comma v in v of x1, if u comma v is an edge of x1, if and only if f of u comma f of v is an edge of E of x2, means edge of x2. That means two graphs are said to be isomorphic if there is a mapping such that the mapping is from vertex set of x1 to vertex set of x2 such that that is 1 1 and onto. Also it preserves the adjacency relationship, that is if u v is an edge of x1, then f of u and f of v is an edge of x2. Example of isomorphic graphs. The following pairs of graphs are isomorphic. C4, that is cycle graph with 4 vertices, and K22, these two graphs are isomorphic. If they usually they look different, but actually they are exactly the same. So till now we are reading C4 and K22 separately, but they are exactly same. They are both are isomorphic graphs. Another pair of isomorphic graphs are C4, that is cycle C5, and its complement, that is also again C5, but drawn in a different way. But their union is as we know that their union is entire K5. These two graphs are also isomorphic, but they look different, but they are exactly same. both will have same number of vertices, same number of edges, degrees of all vertices are same, degree sequence, everything is same. Both have only one cycle of length 5. Invariant property, we can often show that two simple graphs are not isomorphic by showing that they do not share a property called invariant under isomorphism. For example, if x1 and x2 are isomorphic, then both have same number of vertices, same number of edges, same degree sequence, etc. This list continues, means they have almost all properties are same. The relation isomorphism between the graphs is an equivalence relation, that is x is always isomorphic to itself. X is isomorphic to y and then y is isomorphic to x. If x is isomorphic to y and y is isomorphic to z, then x is isomorphic to z. It satisfies transitivity property. So, isomorphism between the graphs is an equivalence relation. So, set of all graphs now we can divide into isomorphic classes. So, we are going to get equivalence classes, but they are all going to be on the same number of vertices. So, for a given n, look at all the graphs with n vertices, then look at all equivalence classes of isomorphism. Given a graph, the set of graphs isomorphic to x is called isomorphism class of x. The isomorphism classes partition the set of graphs with vertex set V. The size of isomorphic class containing x is n factorial by cardinality of G, that we will define later, where G is the automorphism group of the graph x, that we not introduced till now, but just realize that isomorphism class contains exactly n factorial by cardinality of G. That is why this automorphism group of the graph is also important, that we will going to define shortly. Examples of 3 regular non-isomorphic graphs is the graphs K33 is isomorphic to prism graph. Prism graph is shown below. Prism graph on 6 vertices, it is like this. If you look at K33 and this graph, both will have same number of edges, degrees of vertices are also same, but still they are not isomorphic. It is easy to see that both graphs have same number of vertices and same number of edges. Also both have same degree sequence, as both are 3 regular, but they are not isomorphic, as the girth of K33 is 4, that is the length of the smallest cycle in K33 is 4, whereas girth of prism graph is 3. One can easily see that in the graph we have a triangle. So, K33 is a bipartite graph, but prism graph is not bipartite graph. As you know that a graph is bipartite if and only if the length of every cycle is even. So, K33 is bipartite graph, whereas prism graph is not bipartite. So, they are not sharing one property, hence they are not isomorphic graphs. It is interesting to show that every 3 regular graph on 6 vertices is isomorphic to one of these graphs. This is left to an exercise. Non-isomorphic graph on 4 vertices. In this example, we are going to find out all non-isomorphic graphs on 4 vertices. There are 11 graphs with 4 vertices which are not isomorphic. In other words, any graph with 4 vertices is isomorphic to one of these 11 graphs. The first graph is, it contains 4 vertices and there are no edges between them. So, the degree of each vertex is 0 in this case. It is a null graph with 4 vertices. Clearly, this first graph is not isomorphic to the second graph. It is easy to see that it contains an edge. So, clearly these two are not isomorphic. Now, these 3 graphs are not isomorphic. Any 2 if I take mutually, they are not isomorphic. Simply because the number of edges itself is saying that no 2 of them are isomorphic. So, now look at that, the fourth graph is disconnected. Of course, all these 4 graphs are disconnected, but the degree of each vertex there is 1. It is a regular graph, whereas remaining graphs, none of the graphs are regular. So, all these 4 also not isomorphic, and this graph also not isomorphic to other graph. So, in this way we can check that all these 11 graphs are not isomorphic. Okay. And if you, for example, if you look at the 11th graph, last graph, it is K4, the degree of each vertex is 3 in that case, and this is not isomorphic to any of these graphs. Like that, with a small effort one can show that any two these graphs are not isomorphic, and these are the all 11 graphs which are not isomorphic. Now, we are going to define a concept called self-complementary graph. A simple graph X is called self-complementary if X or X complement are isomorphic. Both X is isomorphic to X complement, then we will say that this X is a self-complementary graph. The following are first few examples of self-complementary graphs. K1 is isomorphic to itself and its complement is also the same, so they are isomorphic. Path graph P4, now if you look at its complement, then that is also going to be P4. It is because the complete graph K4 contains 6 edges. So, now we do not have an edge between 3 and 4, so that edge will come, and 3 to 2 there is no edge, and 4 to 1 there is no edge, those edges will come. So, that is again isomorphic to P4. So, its complement is isomorphic to itself. So, this is a self-complementary graph. Similarly, C5 also isomorphic to itself. There is another graph with 5 vertices isomorphic to itself. This graph is called A graph, it is like a shape of A. So, all these graphs are self-complementary, that means they are isomorphic to their complements. So, one of the interesting result about self-complementary graphs is that if a simple graph on n vertices is self-complementary, then 4 divides n into n minus 1. That is, the proof goes like this. Let X be a self-complementary graph on n vertices, then X is isomorphic to its complement. We are assuming X is self-complementary graph, so X is isomorphic to its complement. So, the number of edges in X and X complement are equal. Since they are isomorphic have same number of edges, same number of vertices and so on. So, X and X complement have same number of edges, say k. Further, we know that X union X complement is equal to Kn, the complete graph with n vertices. Hence, 2k is equal to n into n minus 1 by 2. So, total number of edges in Kn is n into n minus 1 by 2. The number of edges in X is k as well as X complement is k. So, 2k is equal to n into n minus 1 by 2, or equivalently n into n minus 1 is equal to 4k. The converse of above result is not true, that is, the graph C4 satisfies that 4 divides 12 n into n minus 1, but it is not a self-complementary graph. It is because its complement is even disconnected. It has having only 2 edges, whereas C4 has 4 edges. Clearly, it is not a self-complementary graph, but 4 divides n into n minus 1 12. So, converse is of a previous result is not true. Let X be a self-complementary graph on n vertices, and 4, then we already proved that 4 divides n into n minus 1, but the numbers n and n minus 1 are co-prime, and hence co-prime means the GCD of n comma n minus 1 is 1, hence either 4 divides n or 4 divides n minus 1. Further, one can see that one of them is even, other is odd. So, either n is of the form 4k or 4k plus 1. So, this is an important thing, that if X is a self complementary graph, then the number of then with n vertices, then n is of the form either 4k or 4k plus 1. So, if there is any graph with n vertices and that n is of the form 4k plus 2 or 4k plus 3, then that is no longer a self complementary graph. This is a necessary condition on the graph with n vertices such that graph is self complementary. Now, we will going to see few exercises. The first question is, for what values of n the cycle graph Cn is self complementary. So, we already know that at least for one value we know that it is self complementary. For n is equal to 5, we saw already that example. It is not self complementary, but n is equal to 3 or n is equal to 4, that we already saw. So, it is better to see the remaining values, and again from the previous result it is sufficient to check only for n is equal to 4k and 4k plus 1. So, it is a nice exercise to find out for what values of n it is self complementary. Now, the next question is, can a graph with 7 vertices is isomorphic to its complement? So, clearly this result is trivial to show because of the previous result. It is isomorphic to its complement means it is self complementary and having 7 vertices. 7 vertices means the number of vertices is of the form 4k plus 3. So, clearly it is not self complementary. So, proof is already done, and this is little difficult to show. So, one has to use pen and paper. Show that the line graph of K33 is self complementary. So, we need to find out line graph of K33 and we need to show that that is self complementary. And also Pele graphs, which we discussed in the second module, these are also self complementary graphs. These are the nice non-trivial examples of self complementary graphs. Just now we saw different examples of isomorphic graphs and non-isomorphic graphs. We also see a concept of self complementary graph. A graph is said to be self complementary graph if it is isomorphic to its complement. We saw several examples of self complementary graphs, and we also saw a necessary condition on the number of vertices on the self complementary graph. Now, we are going to see a procedure to produce self complementary graphs. We also going to introduce the concept of automorphism of a graph. Now, we will see procedure to produce some self complementary graphs. The step 1 is, let P4 be path graph with vertices V1, V2, V3, V4. Let Y be any self complementary graph. So, in the step 1 we choose just a path graph P4. We already know that P4 is a self complementary graph with vertices V1, V2, V3, V4, and Y is any self complementary graph. That means Y we can choose as cycle graph C5 or A graph or any other, any Pali graph like that. Now, the step 2 what we have to do is join the vertices V2 and V3 of degree 2 of the path graph P4 to all the vertices of Y. Then it is easy to see that the resulting graph will have modulus of V of Y plus 4 vertices and is self complementary. So, one has to check the graph is, the resulting graph is a self complementary graph. For example, we know that cycle graph C5 is self complementary. Hence, using the above procedure, the following graph is self complementary graph on 9 vertices. So, here it is defined like this. First, we took the path graph with 4 vertices and a cycle graph here, and then we joined all the vertices of the cycle graph to 2 vertices of the path graph, which are of degree 2. So, we leave the pendant vertices as it is. Now, it is a easy exercise to check that this graph is a self complementary graph, and clearly one can see that it has 9 vertices. That condition is also satisfied, that is n value is either 4n or 4k plus 1, that is satisfied. Automorphism of a graph, the problem that two graphs are isomorphic or not can be converted into finding an automorphism group of a graph. The definition of an automorphism of a graph: automorphism of a graph, an isomorphism from the graph x to itself is called an automorphism. That means we need to find out a mapping from vertex set of x to vertex set of x such that that is 1 1 on 2 and also it preserves the adjacency. So, automorphism is simply a mapping first and it is from vertex set to vertex set. So, it is a permutation actually. So, it is a 1 1 on 2 mapping on the same set, that is V of x. An automorphism is therefore a permutation of vertices of x that maps edges to edges and non-edges to non-edges. G is equal to automorphism of x, the set of all automorphisms of x, then it is easy to verify that G forms a group and is called automorphism group of x. So, if you collect all automorphisms, that is all mappings from vertex set of x to vertex of set of x satisfying the properties that is preserves the adjacency, those mappings, then those collections forms a group. It is called automorphism group of the graph x. A graph is said to be asymmetric if its automorphism group consists only identity. It is easy to see that identity is always an automorphism, but if for a graph identity is the only automorphism, then it is called an asymmetric graph. The following graph is the smallest asymmetric graph. So, here this is the graph. So, this is drawn in such a way that its only automorphism is identity, no other. So, this is an example of an asymmetric graph. It is easy to verify that automorphism of Kn is equal to Sn, which is also equal to automorphism of Kn complement. Kn complement, generally we are denoting Kn complement as Kn power c. So, Kn complement is nothing but the null graph. So, for the null graph as well as for the complete graph, the automorphism group is entire Sn. In fact, these are the only graphs with n vertices such that whose automorphism group is completely equal to Sn. So, this is another way to characterize whether a given graph is complete graph or not. So, and it is easy to see that this means that in the complete graph we cannot distinguish any vertex to any other vertex, all vertices are same, and automorphism group of Cn is D to n, that is a dihedral group consisting of only 2n elements. For any x, any vertex of V and any automorphism G of automorphism of x, then it is easy to show that as an exercise that degree of x equal to degree of G of x. Thus, automorphism group of a graph permutes the vertices of equal degree among themselves. If x comma y are any two vertices of a graph x and G is any automorphism, then it is easy to verify that the distance between x and y is equal to distance between G of x and G of y. That means once you permute the vertices, we will get a different graph. So, the distance of x y in the original graph x is equal to the distance of g x g y in the new graph. So, d of x y is the length of the shortest path between x and y that we already defined. So, automorphisms takes vertices of the same distance to same distance. So, this is another property. So, automorphism maps vertices of same degree to same degree, also it maps vertices of the same distance also. It can be easily verified that automorphism group of x equal to automorphism group of its complement. That is, automorphism group of a graph is equal to its complement graph. It is also easy to verify. This is a nice property, though the graph x and x complement are not isomorphic, but their automorphism groups are isomorphic always. If x is a directed graph, then the automorphism preserves the direction of edges as well. Just preserving like undirected graph is not sufficient. If a graph is a directed graph, then automorphism has to preserve direction also, that is also important. So, because that in the directed graphs it is possible to get more asymmetric graphs. Example of a regular asymmetric graph. We now give an example of a regular asymmetric graph. If you look at this graph, the degree of each vertex in this graph is 3. Now, we are going to show that the only automorphism of this graph is simply identity. So, the proof goes like this. In the above graph, if you look at, we have to prove that every automorphism fixes all the vertices. So, that means there is only one automorphism, that is identity automorphism. To do that, we will provide special properties of each vertex. Then only we can show that that vertex cannot be mapped to any other vertex. So, there is no mapping which takes this vertex to any other vertex. There are exactly two triangles ADE and IJK. Look at the graph here. ADE and IJK are the only two triangles in this graph, and G is the only vertex having no neighbor on the triangle. Again, if you see the diagram, G is not adjacent to any vertex which lies on the triangles AED or IJK, and I is the only vertex, L is the only vertex with neighbors both on the triangle. Similarly, F is the unique neighbor of both G and L. Like that, each vertex has a unique feature. That is why it is difficult to map one vertex to some other vertex. Thus, if you fix these three vertices, that is namely F, G and L, then it is easy to show that other vertices also need to be fixed. So, that is why there is only one automorphism. Hence, the graph given in the previous slide is a symmetric graph, but it is a regular graph. Now, we are going to consider two problems, two algorithmic problems. The first one is graph isomorphism problem. The instance for graph isomorphism problem is that two graphs x and y. The question is x is isomorphic to y? So, we have two graphs x and y, we need to show that, we need to find out whether these are isomorphic or not. Note that it is sufficient to consider both graphs are connected. If the graphs are disconnected, it is sufficient to show the connected components are isomorphic or not. As automorphism group of a graph is equal to its complement, so it is sufficient to, we know that either given graph x is connected or its complement is connected. So, if x is isomorphic to y, then x complement is also isomorphic to y complement. So, hence it is sufficient to assume that both graphs are connected. Further, every graph Z, either Z or its complement is connected, that is why we are assuming both x and y are connected. Automorphism group of a graph. So, another instance, here the instance is a single graph x is given, output is finding an automorphism of x. So, these are two different problems, algorithmic problems. In the first problem, two graphs are given and we need to find out whether two graphs are isomorphic or not. So, for that we need to just tell yes or no, whereas for the second problem it is not simply yes or no, we need to find all automorphisms of x. That is what we are now stating. First problem is a decision problem, that is output required is yes or no, and the second problem requires output. Both problems are related. They are related in the following way. First problem can be reduced to second. Let Z be a graph which is disjoint union of x and y, then Z has two connected components x and y. If you are able to compute automorphism group of the graph Z, and if that contains a permutation which interchanges two components of Z, that is x and y, then x and y are isomorphic. So, we are able to convert the isomorphism problem to automorphism problem of the graph. An automorphism of a graph is an isomorphism to itself. In this module, we showed that identity mapping is always an automorphism, and if a graph has no other automorphisms than identity, then it is called an asymmetric graph. We also given an example of a three regular graph, which is an asymmetric graph, and we also given a smallest asymmetric graph. Now it is better to see other examples of asymmetric graphs. Now with this we end this module.